First, a couple of announcements. Your assignments or AP testing was due last Friday. You can still pay for it. If you haven't, there will be a late fee. The Alumni Association scholarship is still open, I believe, until November 6th. So there's still time to work on that. The chemotaxis was due Friday. I'm catching up with grading it. Took a little break from grading this weekend. So expect it to be graded beginning of this week, middle of the week. Those grades should be in. There's a couple people that emailed me for asking for an extension on Friday, and recognize that that's okay. At least they let me know, but that was like not what I intended it to be. You should identify that you need more time before the day that it's due, right? So those emails kind of pissed me off. So I'm likely just going to give you a 1 if it isn't turned in by this point, and then delay your grading a bit more because I expected a bit more notice if you needed an extension, right? You all are procrastinating. I'm not going to encourage that. Next up, let's see. So at this point in the semester, we've learned a lot about object-oriented programming, and this is the first of many parts to your asteroids assignment. Due November 6th, which is also the end of the grading period, is like part 0 of your asteroids project. So you're creating the background of the of space or something, and you'll see examples of it. Yeah. So looking forward, that's what we have to do, and we have a new PowerPoint slide to work on. So we'll start with a review of all the things we learned with regards to object-oriented programming, and then we will go over some of the math that's behind the Starfield assignment. Okay, so in the slide in front of you, it gives you some of the tips on what's most difficult for the AP exam. We have this idea of inheritance, like how you inherit traits from your mother or father. Objects work in similar ways. They inherit member variables and member functions from their parents. And this idea of encapsulation, it's a big fancy word for public and private. So if you ever wondered at actually we don't see it in processing, but public and private is kind of related to scoping in that some information is known with regards to other objects and some are hidden. And then the other idea you'll see is this idea of getters and setters. Since some member variables are private, there still needs to be a way to access them or ask permission for that, and we take that in the form of getters and setters. Those tends to be the most difficult parts of object-oriented programming, so hold on to those words. If I say them later in the presentation in the coming weeks, then you'll know to pay attention, eh? All right, so here's your overview of everything we've learned with object-oriented programming. The goal of it is to model real life. By being humans, you know this pattern conceptually. Like this picture in front of you, you wouldn't call this thing a beak, some feathers, wings, legs, and a tail. Instead, you would group it all together into one name, one word that describes this object. So that specific bird from before is a starling, and it's an object, and it has certain data associated with it, and it has certain behaviors associated with it. So some data would be like size, position, and color, things you're very familiar with. Behavior may be like flying around, eating, and sleeping, being the most basic kinds of functions for this bird. And so in object-oriented programming, we write a class to represent it, and that models each of those features of the bird. So the data, we create member variables. For the behavior, we create member functions or member methods. Same thing. I think I prefer to use member functions. We go back to this idea that a class is a blueprint. It says what kinds of data these objects have and what they do, but it doesn't actually make the object just yet. Think back to the blueprint of the houses from the video we watched earlier. In the dice example, we used Bob like a stamp. It's a blueprint. So representing all those ideas in code, you have the skeleton here. You see my mouse, yes? So at the top here, we have these member variables. 3 of them are integers, 1 of them is a double. Down here, we have 3 member functions, the fly, the eat, and the sleep. Fly, eat, sleep, those are member functions, or member methods. So as mentioned before, the blueprint doesn't actually make the object. Describing one of these starlings is very different than creating one. So we have this line of code at the bottom, starling bob equals new starling. This line actually makes a new object. And so on the left-hand side, starling bob, that's the declaration. On the right-hand side, you see the initialization, bob equals new starling. And we put a lot of emphasis on the word new. Now we've actually made that bird and created it, put it into existence. It has been allocated a chunk in the computer's memory. I think last week we started talking about, or we've been talking about constructors, and then we started talking about more complicated constructors. Constructors are the initializers of a object. They set up the object that very first time it's called, so the names of the constructors must match the name of the class exactly. There could be more than one, which we went over last week, a no argument constructor and a many argument constructor, and talked about some differences. So focusing on the constructors, there's a prime example of it, class starling, and now we have starling parentheses in yellow here, that's the constructor. The no argument constructor, which I still haven't asked Mr. Simon whether or not it's the default constructor or not. The no argument constructor here has been initialized to a bunch of random positions between 0 and 300, a random color, or not a random color, it's a certain color, maybe a dark blue, and it has a certain size. Notice that each of the member variables inside the starling class has been initialized here inside the constructor. Here, we enter 2 arguments, right, 2 inputs to our constructor, and now we can now create a starling object at a certain position. We fed in this information to the object. Subtle difference. No information, it's a random position. 2 bits of information, you can specify where it should be. Questions so far? We're reviewing everything you've learned about objects, and we just talked about the constructor. Okay. And along with this idea, right, we've talked about a single object. Now we go ahead and make many objects, which is why we needed the help of an array. So in Java, arrays are actually objects. And I think everything in Java ends up being an object. Pretty sure. Even like the main function or the draw function, those things end up being objects. So when we make an array of objects, let's say it's many objects grouped together, you need to use the new keyword twice. Once in order to make the array, and then once more to put the new objects into said array. So you got practice with this in your latest assignment, chemotexes. So this line of code should look familiar. Bacteria square brackets a bunch equals new bacteria square bracket 10. This line of code makes the apartment buildings. Go back to that analogy, I find it quite helpful. There are 10 empty apartment buildings with this line of code that I've just highlighted. Then, utilizing a for loop, you march through all those apartment buildings and put in a bacteria in each one. This for loop, each apartment building has now been filled. So all those ideas are again synthesized together to this new assignment due next Friday called Starfield. And it's an animation that simulates traveling in space, or fireworks or explosions. You have a point in the center, and then the particles or whatever you want to make them go out from the center. Each point of light moves at a different angle and speed, and you can change the size and or brightness of the points to create 3D effects. So let's see some visual examples of this. This is the source of inspiration, Star Trek. In the opening had this little animation. Notice how the particles move towards you. So there's another example of your Starfield assignment. You have the random bunch of particles. So you'll be utilizing a particle class. And we'll talk about this tomorrow. There will be an oddball particle. So notice there's a little square that sticks out. So that's where we see the ideas of inheritance, and using this keyword extends to build new classes that exist on various existing classes. We're reusing objects that we've made before to make life easier. Easier, quote unquote. It seems really extra when you first learn it. Like, when the heck is this going to be useful? But conceptually, it's something you're going to be tested on, and a big feature of object-oriented programming. So right here, we begin thinking about, okay, the base class is going to be something called a particle. So we ask ourselves, what do particles have and what do particles do? Think to yourself for a couple seconds. What, as we are creating the skeleton for a particle class, what are its member variables? What are its member functions? Okay, so you thought about it. You're probably thinking about like position and speed and some other kinds of things. We'll get back to that. The next couple slides focuses on the kind of mathy movements that occur for a particle, because you're starting from a center and it goes outwards, not in straight lines, but kind of at an angle. What does it remind you of? Like polar coordinates almost. So we'll be utilizing pi and math and sine and cosine to help us get the kind of like path along, like angled motion represented. So pay attention to maybe like this particular particle, right? Notice the path. It's at an angle, but from a centralized point. Okay, and there's a little bit of complicated math going on. So right here, yes, the ideas you'll be implementing utilizing like math sine and math cosine. So here's your central particle. It hasn't moved just yet. It's at a certain position, 320 and 420 for the x and y coordinates. It has a certain angle and speed as denoted here. These things probably going to be random within, like these ones. The angle and speed are somewhat random, but they're individualized to each particle. Notice they're both decimals. Okay. And so here's the formula that gets you the new x direction, or the change in x and the change in y. So you take the cosine of the angle times the speed. That thing will gives you the x component of your particle's motion along like that diagonal. And similarly, sine of the angle times the speed gives you the y component, how much you move in the up and down direction. So calculating these things using your given angle that you're moving at, so from a certain reference, 0 goes left and right this ways. So this is 2.3 degrees, or double check myself. Is it degrees or radians? Probably radians, yeah. I think we're in radians for all this stuff. So radians, that's your angle. multiply it by your speed. So then we have this much change in x and this much change in y for this dot to move from here down to here. Ta-da. Angle and speed stay the same. Those are givens when you create your object, and then utilizing that cosine times speed and sine times speed gets you your x and y directions. Good. Again, y moves positively downwards, right? So not so bad, but when you apply this idea, there's some little subtle things that happen that I still haven't wrapped my head around it that much. Mr. Simon has pointed out because it creates some pretty neat effects. My x, my y, my angle, and my speed, those member variables, should be declared as doubles. And if you do a combination of like ints and floats and doubles with these, you get some pretty weird effects. And I'm still working on understanding it. So Mr. Simon calls it integer quantization. Sounds so fancy. So here, when they're all doubles, it looks like this, right? When you make speed an integer, so then there's some inherent rounding that happens, you get like these, what is it? In chemistry, what do they call them? The little rings, right? So they're grouped together in these bands by having speed as an integer. When you have your x and y as an integer, you make your x and y coordinates are a grid that move out like consistently with one another, which I find somewhat surprising. And if you mix it up, if your angle is an integer, you get this kind of weird motion that I can't quite explain, but looks kind of neat. And so you got to be careful. The subtle differences between like float and double, especially with processing. The ellipse function only works with floats and ints, not so much doubles. So when that occurs, right, as you see here, my x and my y being doubles, it says, oh, we complain. Ellipses like floats. It doesn't want that level of precision for some reason. It's too much number crunching. So one way to fix that is with your good old friend casting. Chop off those last couple decimal places, jam it into the ellipse function. Suddenly it's a float, now you work. So Mondays tend to be a lot of information because Mr. Simon and I are of the philosophy that we want to get you all started early on these assignments, and by going over these slides, you know enough to get like one particle starting to move like diagonally from like the center point. So that's why we talk about so much stuff on Mondays or Tuesdays, and then we kind of slow it down as the week progresses. So apologies if you're feeling fast-paced, that is intentional, so you can, for those that want to get started, they can get started. Instead of having to wait like halfway through the week and then suddenly like out of a 2-week assignment after 1 week, then you start, so really you only have 1 week to get started on it, and that's not what we want. Then the other parts, once you know that complicated math, you make an array, you do the same as before, bob square bracket I dot move, bob square bracket I dot show inside a loop to move each particle. And you're like not too far from creating or finishing up this assignment. Do I want to talk about this? Yes, sure. So particles, they all start at a centralized point. We're narrowing in our scope to the constructor. I'm still good with time. Initializing speed, angle, and color. You want to change it just once. Create it just once randomly in the beginning per particle, and then make sure angle, speed, and color stay the same. Unless you want epilepsy-inducing particles, then you would change the color. And then how many arguments would the constructor need? Well, that's debatable on what you want to do with it. So there you go. Some examples. Integer color. 1, 2, 3, 4, x, y, speed, and angle, those are all doubles. How much do you expect? How many lines of code do you expect to see in the constructor? You look at the number of member variables. There are 5 things, so there should be 5 lines of code for the particle inside this particle constructor. And so, a code segment to get you started. You start my x and my y at the center of your screen. You choose some kind of random angle based on math.py. Speed is random. Make sure to keep it a decimal, not too fast. And then your color has random, and so that line of code looks familiar. All right, so with Tuesday, we show you more examples of, actually for you it's Wednesday. Wednesday, we show you more examples of the Starfield assignment. Please look at the assignment prompt in GitHub. And you can get started by making a single particle move from a centralized point. Yeah, use that math.sine and math.cosine. That's all for today's lecture. Have a good Monday. Review this video recording at your own leisure.